All right, so that kind of sums up, that's probably the very quick kind of introduction to soil colloid chemistry and why it's important, because it holds the nutrients that our plants need in order to grow. You saw in there that we're talking about that the CEC in the surface area, and so this is where our clay, our texture comes in, that we have sand, silts, and clays. And then if we have more clay content, we have a larger surface area. On our surface charges, we have both positive and negatives, but in general, the overall net charge is negative. So the overall charge on soils is typically negative. As you can see by this small diagram, and each one of those cations are being held to the negative charge in the soil. Kind of like a magnet. Like this is just simple magnetism through electronegativity. There's this ionic double layer, so you have all of these nutrients and they're all real close to the soil colloid and they're all vying to be held there. They're all like trying to, they need to be attracted to something, and so those charges are going to, there may be a little bit of extra charge that is shared between this positive, this cation and that anion, and this is constantly moving. In soil chemistry, they're actually studying the oscillations and trying to figure out how they can manipulate this so that we can get more of the positives in here, and that's a whole different area. They get very microscopic, and there are people that spend most of their career studying that thing, and they're never gonna figure it out. They're never gonna figure it out because it changes so much. So we have cation exchange capacity, and so that is gonna be between this cation and some negatively charged material. And so we have a few cations that are the primary ones that we find in soils that are part of that C. Hopkins Cafe managed by my cousin, Mokul Nina. And because they each have this charge and they have a certain affinity for water, the amount of charge and the amount of water that is around them is going to influence how strongly they are attracted to that soil colloid. So and I'm gonna set this up a little bit, I'm gonna set this up for when we move into talking about pH. So hydrogen and aluminum are our acidic cations. Hydrogen and aluminum are our acidic cations. Everything to the right, these are considered our base cations. And these are what give us our alkaline soils. We apply lime, which is calcium hydroxide or calcium carbonate. Maybe it's calcium magnesium carbonate. And we're also applying potassium and sodium and some ammonium fertilizers. So our acidic cations are going to balance with our base cations, and that's what gives us our pH. They were talking about the anions such as nitrate, phosphates, sulfates, and then chlorine that we really don't focus too much on because we're not applying salt to straight salt to our soils. Although I want to, I have this theory that we can possibly kill weeds by just spraying salt water. I haven't tested it yet, but it would make sense that if you spray salt water on plants that they would die, because that osmotic potential would pull the water out of the plant, and hopefully the grass would grow back instead of that weed plant. I would have to think that there are scientists that have been studying this thing a lot longer than I have, and therefore you would think they would have thought of this already. So not really quite sure how that works out. I've got some great ideas, but none of them have worked out so great. So they were talking about in that video that in the tropics in like Brazil, they have a big problem with this because their soils are highly weathered. And so we have oxasols in that region and ultrasols that have gone through this weathering process, and there's nothing left there but aluminum. And we'll see that in a couple of slides when we talk about the structure of our clay colloids. So what they do is they're going to apply phosphorus because their plants are deficient, and the soils won't give that phosphorus up so the plants can take it up. And so they'll apply a lot of lime, but they can't get that pH to move up above 4.5, which is very low. And so they can't grow any plants, and so they keep putting phosphorus on, and soils have such a large buffering capacity that they can buffer against the lime application, they can buffer against all the phosphorus you can throw at it, and they're just wasting money, and their plants aren't growing anything. So in our more highly weathered soils, we have problems with a stronger anion exchange capacity rather than a cation exchange capacity. Adsorption and absorption. I finally remembered to bring my tape and my hand sanitizer. And so, kind of similar to adhesion, is that adsorption with a D is going to be the attraction between two unlike surfaces or oppositely charged surfaces of a particle. And so when I think of adsorption, I kind of think of it similar to a piece of tape that I have this, I'll wait for y'all to finish that. I'm gonna try to go a little bit slower on this. You got the notes, Andrew? You need a note packet?
No, I got it. I'm just looking for the slide.
Okay. Got it? Cool. Okay. All right, adsorption, kind of like adhesion, attraction to an oppositely charged particle or not the same. So in adsorption, if this piece of tape were my cation and my finger was the soil colloid, this piece of tape can desorb from one piece of, or one clay colloid to another clay colloid, and it can go back and forth. And it can move to a different one, and that's how nutrients move to plants. So adsorption with a B is going to be an attraction between oppositely charged particles, surfaces on particles, but it is not taken up, it is just held onto that soil colloid. Absorption with a B is much different. Absorption is like when we apply hand sanitizer, and once that hand sanitizer absorbs, or even lotion, absorbs with a B into my skin, we cannot get it back out. So once the nutrients are desorbed from the soil colloid, they are absorbed with a B into the plant. The plant does not necessarily take up calcium and then give calcium back. Hydrogen it might, and that's a whole different process with their physiology, with plant physiology and the way that they operate. But for soil's sake, once that nutrient desorbs off the soil into the plant, it is not likely to be given back after it has been absorbed. Now the plant will die, decompose, and within that organic matter, the nutrient that it absorbed will be released back into the soil and then be adsorbed to soil colloids or organic matter. So we have this process, this decomposition, where plants will start to take these nutrients up, and when they die, they will put them back. So we do this with cover crops. Does anybody plant cover crops? No? So we'll plant cover crops in the fall so that we don't leach any of our nutrients out. And those cover crops will continue to absorb those nutrients over the winter. And when we go to plant our corn in the spring, we'll kill the cover crop and it'll die and put some nutrients back into the soil. So we're trying to maintain or not lose the nutrients that we've applied from the previous crop, because they're still there. But if we have enough rainfall, which we have in the winter and the fall, we can lose those nutrients. We have these 4 different types of soil colloids. We are mostly interested in this crystalline silicate. These are going to be our kaolinites, our smectites, vermiculites. We have non-crystalline silicate from our andesols that are mostly from volcanic eruptions, volcanic ash. They have a different structure than these ones that have been formed over time. We have these aluminum and iron oxyhydroxides. So these are highly weathered soils. When we have aluminum and iron oxyhydroxides, those soils are highly weathered. The only thing left are going to be what? Aluminum and iron. The only thing left there. But aluminum and iron typically have a charge of +3. So they can hold on to 3 of those nitrates or 3 of those phosphate anions. And we'll be concerned with kind of the organic matter or the humus, mostly in our histosols, but they play a large role because we need to keep that water in the soil because that's how our nutrients move into the plant. They'll have both CEC, cation exchange capacity, and anion exchange capacity, and I'm going to go over this in a moment. But the charge is always negative. Here are a look at some of the properties of some of these soil colloids. And so if you were farming on a kaolinitic soil, would you consider this, I'm referencing back to the video, is this a large cup or a small cup? Kaolinite. Small cup. What about vermiculite? Large cup. What about organic matter? Extra large cup. So having these 3 different things in our soils are going to allow us to have better production or maybe change our best management practices. And if you can remember back in our classification, we may have this fine, silty, kaolinitic, thermic, typic, paleoudal, which would tell me that there's some kaolinite in it, or it might be smectitic. There are different little things in there that tell me about what I can expect that CEC to be just by looking at the soil, just by looking at the classification. I have some indication of what I might need to do to that soil before I ever even get there. I'm on Web Soil Survey, I look at the taxonomic classification, and I can tell all these things about it, and I haven't even showed up to the field. I get to Hannah's field and I go, you've got blah, 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 blah. I sound like I know what I'm talking about. The soil test comes back and confirms that I did know what I was talking about. Like, it's those types of things that you might run into. All right, so we have 2 of these fundamental structures within our soils, within our soil colloids. We have a tetrahedral and an octahedral. For our tetrahedral, the silica is going to be our central atom, so that's +4, which balances out the 4 oxygens that are surrounding it. It kind of looks like a pyramid. We'll go over that in the next slide. It looks like a pyramid, and in the center there is this atom that gives it the balance. Our octahedral looks like 2 of those pyramids put on top of each other. And we will have either aluminum or magnesium as the central ion. And those 2 can substitute for each other, which is going to change the charge of that particular structure. So we're talking less than electron scanning microscope. What I didn't like about chemistry was it's really kind of all theory. You can't really see those atoms, can you? I just don't trust that you know what you're talking about because you can't show me all the little orbitals and all the little electrons floating around there. What you have is a diagram of what you think it might be. Not that I'm any smarter, but when I was in chemistry, I just didn't believe that. So I am trusting the people who came before me that say that this structure works. So here we have our tetrahedral, where we have this silicon in the center. Our oxygens form a tetrahedron, or what looks like a pyramid. We have this octahedral that has either aluminum or magnesium, and this hydroxide. So we have an OH group on the edge of that structure. That's about as chemical as I get here. This is probably the most chemistry that you're going to encounter for this class, maybe till we get to module 4. So what we have is this looks like a 2-to-1 clay, where we have 2 tetrahedral sheets and an octahedral sheet in the center, kind of like a sandwich. We have the pieces of bread and the meat in the middle. Again, a different look at that. So we would have this 1-to-1 type mineral, or this kaolinite, where we have 1 piece of bread and meat, or 1 tetrahedral, 1 octahedral. There will be another tetrahedral and octahedral underneath it. Another tetrahedral and octahedral underneath it. In this 2-to-1, just like I mentioned before, we have this sandwich, and we will have another 2-to-1 underneath it, and the bonds will be shared. These will be held together through hydrogen bonding between what would be the bottom of this tetrahedral sheet and the top of the next tetrahedral sheet. So for our 1-to-1 kaolinitic soils, we have low charge, so we have small cup. The charge is going to be on the edge of those sheets. Hold on, I'm going to go back just a little bit. The charges are going to be right here. This is where the charge is going to be on a tetrahedral. And our low CEC, prime indicator that you have a kaolinitic soil. Very low CEC. These are the red clays that we use to make buildings on. This is what's on your softball field. This is what's on the baseball field. It does not move, it doesn't shift. Once you pack it down, it's packed down, and there's not a whole lot you can do about it. For our production and agriculture, we need to have a nutrient management plan or a strategy that says, we apply some soil chemistry to this and we figure out how much the plant is going to take up over a period of time, let's say a month, 2 months. What do we expect the plant to absorb? And then how much do we need to apply back to replenish that, what was taken up? So here we have a 1-to-1, our tetrahedral on the top, here's our octahedral, and we have these hydrogen bonds that do not allow the expansion of these 2 1-to-1 minerals. So they don't move, they don't shift. That's why we build on them, because they're not gonna move, they're not gonna budge. Have you ever driven down a road and wondered why it undulates like that? They didn't build it that way. They had some 2-to-1 clays underneath there, or they didn't build it with 1-to-1 clay, and that soil shifted and settled. Or you might see a building that's cracked at the top. Or you might see it's cracked on the outside, and you go, how did that happen? Well, because the soil underneath the foundation shifted a little bit. And if they had built it on this type of soil, it wouldn't have shifted. Next, we have our 2-to-1 clays. And these are going to have a high negative charge. And we're going to talk about this isomorphic substitution in just a moment. But we can have this substitution for different elements inside of each one of those tetrahedral and octahedral structures. Now, we don't go out there and apply more aluminum to a soil and this changes. This actually happened when that when the magma came out of the volcano, as lava, underwent the rock cycle, and whatever metals were in that lava is how these structures formed. So long time ago, this is permanent charge. This is not likely to change because of the way that that structure was made 400 million years ago. In the octahedral, we'll get aluminum and magnesium to be changed, to exchange. And when we see that we have a high CEC, we're going to think 2-to-1 expanding clays, so smetite or vermiculites. And this happens because we can get some water that moves in between those two sandwiches. So if this was a 2-to-1, looks like a sandwich, this is a 2-to-1, some water can move in there and expand a little bit, kind of like a swell. So here we have, this is our 2-to-1, our tetrahedral, octahedral with likely to be aluminum 3+ in the middle. We have another 2-to-1 on top of it, and water is able to kind of seep in between those two hydroxyls. Because remember, in our octahedral, there's a hydroxyl group on the end of this. So the water can move in and kind of open that up just a little bit. Remember, electron microscopic level. Within each one of those 2-to-1 silicate clays, we have something like a mica. But what happens is, here we have both of our 2-to-1s, and so that clay expands, and if you have enough potassium in there, the way that those tetrahedral and octahedral are kind of put together, they're very symmetrical, but they form this kind of a hole in the middle of that structure. And that potassium is perfectly sized to fit inside of that hole. And it's positively charged, so it's automatically attracted there. So we have this expansion, water moves in that has some of that potassium in it, and when the water is removed, it sinks down. Because now there's not that expansion, so it'll shrink back down, and that potassium is now trapped inside of that little hole. And the only way to get it back out is for more water to come in. But guess what the water has in it? What did it have in it the first time? Has more potassium. So it's not like the potassium is going to come out of this charge right here and move back into the water. So if you have micas, you're going to have potassium fixation or possibly ammonium fixation. Chlorites, not likely to encounter these, but we have two sandwiches that are now bound together by this octahedral layer. And those are not expanding, similar to our 1-to-1s. All the charges are taken up now. There's no room for water to come in here because this octahedral layer has now taken the place of that. Is there anything to write down on this one? Okay. And then a look at all of those together. You will likely have to identify the structure of kaolinite, vermiculite, the micas. You'll probably get this cut up as a picture and say which structure does this look like? Which one is this? Is this a kaolinite, or is it a montmorillonite or smetite? Here's going to be your indicator for micas. Mike with a K, right? I had to use those little mnemonics to remind me that mica is going to trap that potassium. Here are aluminum and oxyhydroxides. All they are is, they're basically octahedron, an octahedral layer with an aluminum, and then another octahedral layer with an aluminum. There's no tetrahedral that binds that together. But this aluminum, the charge is so great that it kind of transfers some of that in this region right here, it will change, it will transfer some of that charge and be held together by hydrogen bonding. Anybody taking organic chemistry? She just looked at me like, please don't say that. Tough stuff, isn't it? I hated organic chemistry. Hated it. Like, for what? For what? What for? How does it, what they do is they teach you all this stuff, they don't tell you where to apply it at. Okay, great, potassium hydroxide, and then what am I supposed to do with that? What's up? Right. So, the main thing we need to know is that this structure is not something I want to draw ever, and you won't have to. But we do know that the charges are going to be net negative. Where net negative? No one knows, not even them. So what they do is they make organic chemistry hard enough that you never want to talk to them ever again about it. That's what I promise you, that's what they do. I can remember when I was in graduate school, I was like, listen, if I know organic chemistry and I can talk statistics, no one will ever want to come by my office ever again. Those two things people do not want to listen to. So we have these hydrophobic and hydrophilic sites on this, and what do hydrophobic sites mean? What is hydrophobic? Water repelling, and hydrophilic? Water loving. So this is why we have so much of our water holding capacity and our CEC tied up in organic matter. When we're talking about sources of charge, I'm hoping I can make it into, all right, we'll just get through isomorphic substitution. Iso, meaning similar. Morphic, meaning size and shape. This has zero to do with the charge, none. However, the charge has everything to do with the CEC of that soil. We are really just talking about a size substitution to fill a gap, which is in the central atom of either the tetrahedral or the octahedral. Not the charge, size. And so in the tetrahedral, we'll have silica replaced by aluminum. Now remember, this happens 400 million years ago. We can't go out and apply aluminum and change the way this structure the silicon structure is. We can't apply more magnesium and have some substitution in the octahedral layer. It's permanent charge. Oxygen is worth -2. It has a valence of -2. Always -2. She's back there shaking her head. Just doing a little simple math here to show you where the charge change. This is like bank account type stuff. So in our tetrahedron, we have 4 oxygens, which are going to be, what charge is that going to be? Negative.
-2.
And we have 4 of those. So what's the overall? -8. And our silica is +4. Integers, math. -8 + 4 is -4. Very simple. In our octahedron, we have 6 oxygens worth -12, and we have aluminum 3+, which gives our net charge -9. So if we have this large tetrahedral and octahedral layer, our one-to-one clays, we add up all the oxygens, we add up the charges of the silica and the aluminum. I did the math for us, so we have our oxygens, there's 17 of them worth -24, our positive charges are +24, and the overall charge is 10. But if we change that, I'm going to show you the difference in the isomorphic substitution now. I did the math for us. We have 7 oxygens on the top, oxygen, oxygen, oxygen. -14, -28, and 20 is -48. Oh, are y'all filling this in? Yeah, okay, cool. So oxygens across the top, we have 7. Typically, the way I do this is I count the oxygens and multiply by 2, that's negative. We have 5 oxygens here. Ten there, and 7 there. So the overall net negative, the overall negative component of this is negative 48. 3 silica, 4 aluminums, plus 36, the charge is negative 12. Did I go through that too fast? Okay. Y'all do the other side. Did you have fun yesterday, Sam? Did you have fun? Kind of? Good thing we talked about how to do those calculations,
Yes,
right?
yes.
But notice the charge change. Because we had the substitution, the charge now changes. And we have more cation exchange capacity. So here we had a small cup. And then here we got the medium cup. A little bit. Now remember, again, this happened 400 million years ago. We can't affect this, but to understand that this is where we get that charge from, that it's not always consistent. And you gotta think about lava and the way it, what's up, Henry?
I got 21.
So negative 14 and negative 14 is negative 28.
48.
And then 9 and 9 is 18. Plus 8 is 26. 48 minus 26. Or negative 48 plus 26. So it can get real tricky in here when you start substituting. We have aluminum, magnesium, aluminum, magnesium, magnesium, aluminum. Again, microscopic level, I have to trust they know what they're talking about. Because I'm over here trying to spread salt water on plants and replace glyphosate. Not the sharpest tool in the shed. But just a kind of an understanding about how this thing happened 400 million years ago when that rock broke and the soil started to form, the way that that rock was made,